So students, after the discussion of Young's modulus, our next topic is the stress strain curve for a metallic wire. So whenever we are loading a wire, we know that within the elastic limit, the ratio of longitudinal stress to the longitudinal strain is a constant quantity, and that is known as the Hooke's law. Now in this graph, we'll study the behavior of a metallic wire when we are loading that metallic wire. Now you can see from the graph, when the strain is small, that is less than 1%, then the initial part OA of the graph is a straight line, and it is showing that stress is directly proportional to strain, and the wire is obeying the Hooke's law up to the point A, and this point A is called the proportional limit, where the stress is proportional to the strain. Now when we further increase the load in the region from A to B, the stress strain graph is now slightly curved, and the stress is not proportional to strain. Now if the load is removed at any point from O to B, in that case the graph is retraced along BAO, and the wire again regain its original length. So the portion OB of graph is called the elastic region, and this point B is called elastic limit or yield point, and the stress corresponding to this point B is called yield strength. Now if the wire is further stretched beyond the elastic limit, the strain increases rapidly even after for a small change in stress. So if load is removed at any point, suppose that at point C the wire does not come back to its original length but traces the dash curve, that is CO dash. So even we are reducing the stress to zero, in this case some amount of strain that is equals to OO dash is left in the wire. It remains in the wire. So there is some sort of permanent set or permanent increase in the length, and the wire is said to have acquired a permanent set. And this non-reversing strain is known as the elastic hysteresis, and we are going to discuss this elastic hysteresis in our later on topics. Now if we further increase the load beyond C, then it produces a large amount of strain or increase in the length of wire. The stress corresponding to the highest point D is known as the ultimate strength or the tensile strength of the material, and you know that the tensile strength is the ratio of maximum load to which the wire can be subjected by slowly increasing the load to the original area of the cross section of wire. Now beyond this point D, that is the tensile strength point, the thinning of wire is not uniform. Now the wire is developing the kinks at few points along its length, and some additional strain is produced even when we are unloading, that is we are reducing the load, and finally what is happening, the wire break at a fracture point, that is E. So in the region between B and E, from B to E, the length of wire goes on increasing even without any addition of load. And this region is called the plastic region, and the material is said to undergo the plastic flow or the plastic deformation. So this is how the metallic wire is behaving when we are increasing strain on the wire. So initially it is obeying the Hooke's law, and finally beyond a certain limit a fracture point reaches where the wire breaks at a particular point. Now let us find out the Young's modulus of a wire when we are loading that wire. So in order to discuss this, let us perform an experiment. In this experimental setup, we are having a metallic wire which is having two long straight wire. Of course you can see in this figure that we are having two long straight wire with same length and equal radius. Now we are suspending these wire side by side to the fixed ends A and B. Now the wire A here is called the reference wire, because in reference to this wire we are observing the change in wire B. Now this wire A carries a main milliammeter scale, that is M, you can see, and below it a very heavy load is fixed. Now this load keeps the wires tight and free from any kink. Now the wire B is called the experimental wire, which carries a vernier scale. You will study about this vernier scale once the school will get open, and you will perform experiments based on this vernier scale. Now vernier scale is helpful in measuring the small length, that is of the order of millimeter. So this vernier scale can slide against the main scale attached to the reference wire. A hanger is attached at the lower end of this vernier scale V, and slotted weights are attached to it in this hanger. So we can slip the weight of half kg one by one to this attached slotted hanger. Now with the help of screw gauze, the radius of this experimental wire can be measured at different places, and we can take the mean of the radius. Now L is the length of this experimental wire, and for a small initial load, let the load is 1 kg, we are putting that load on this hanger. Now this initial load keeps this wire straight and without any kink. Now we are observing the reading in this vernier scale, and again we are adding half kg weight to this hanger. Now this half kg weight elongate this wire for a minute, and the difference between the vernier scale previous and the current will give the extension produced due to this addition half kg weight. Now the weight is further increased, again we are adding further half kg, and again we are observing the vernier scale reading, and every time we are adding the weight on this hanger and we are observing the reading in vernier scale. Then what we are observing here? We are observing, as we know that the stress produced, or the formula for stress is force upon area. So M is the mass and G is the acceleration due to gravity. So this represents the force, downward force acting on the extension wire, experimental wire. Also we know that stress is equals to change in length upon the original length. So we know that formula for Young's wire is stress upon strain, and after substituting the values we are having this Young's modulus for this particular experiment comes out to be L upon pi r square tan theta. Now this tan theta is what we are obtaining from this load extension graph. As we are loading this experimental wire, we are observing the observations and we plot these on a graph. Now what we are observing that when the load is increased, the extension produced is proportional to the load applied. Now from this we are obtaining theta and substituting that in the previous formula of Young's modulus, that is y is equals to L upon pi r square tan theta, and we are obtaining the value of Young's modulus for this wire. Now after finding out the Young's modulus for a given metallic wire and discussing the stress strain curve, now we can classify the materials on the basis of the stress strain curve we had discussed earlier. So basically we can divide the metals in three main categories. Number one, the ductile material, the material which have large plastic range of extension, they are known as the ductile material. Brittle material, the material which have very small range of plastic extension, they are known as the brittle materials. And the malleable materials. So we can compress the solid substance and there reaches a stage beyond which it cannot recover its original shape after the deforming force is removed. So we are beating the substance and converting that into a sheet. So those substances are known as the malleable materials. Now let us first discuss the ductile material. So you can see from this graph that there is a fracture point and this fracture point is widely separated from the elastic limit. That is, the point A is far from the point E. E point is our breaking point, fracture point, and A is the elastic limit for this particular metallic material. Now these material undergo an irreversible increase in length before breaking. So they can be drawn into thin wire. For example, we are having copper, silver, iron, aluminium, etc. So this is the beneficial portion for obtaining the ductile material. So the range for ductile material between the elastic limit and the breaking point should be very large. Now our next type of materials are the brittle material. Now you can see from this graph that these brittle material breaks as soon as the stress is increased beyond the elastic limit, and you can see from the graph that the breaking point is very close to the elastic limit. So they break easily beyond the elastic limit. Now examples for the brittle material are the cast iron, the glass, ceramic, etc. Our next type of materials are the malleable materials. Now in these malleable material, as you can see from the graph, we are having the compression. So we are compressing, we are applying the force on the material and we are compressing that material. So that's why we are having this kind of graph. Now you can see from the graph that elastic limit A is A dash for the compression material. So we are taking the symbol A dash over here. Now beyond this elastic limit, if the force is being removed, in that case the behave is solid substances behaving as a plastic body, and the yield point B dash is obtained under the compression, and which is known as the crushing point. That is, we are applying the force on the object and the object is being crushed beyond this elastic limit. Now, after this crushing point, the metal is said to be malleable, that is, they can be hammered or rolled into thin sheets. For example, we are having so many materials around us which are malleable. For example, gold, silver, lead, etc. Apart from these three main kind of metallic substances, we are having another substance which are known as the elastomers. Now, what are these elastomers? The material which can be elastically stretched to large values of strain, they are known as elastomers. For example, if we consider rubber, a rubber can be stretched to several times its original length, but still it can regain its original length. So when the force is removed, the rubber regain its original length. So there is no definite plastic region for this rubber, and rubber just break when pulled beyond a certain limit. So its Young's modulus is very small as compared to the Young's modulus of the strain, that is the metallic wire. Suppose if we are considering or comparing rubber with the steel. So elastic region for this rubber is very large, but this rubber is not obeying the Hooke's law. In our body, we are having the elastic tissue of aorta, and which is elastomer. So we are having a graph for the elastomers, and you can see from this graph that strain is increased for small stress, and beyond a particular point, that is the elastic limit for this elastomer, there is break in that. Now the graph is not a uniform linear graph, so we are observing from this graph that the elastomers are not obeying the Hooke's law. So initially for a small stress there is large strain in the object, but beyond that is elastic limit for a small stress, again the strain is increased rapidly and reaching an infinite point. Now our next topic is the bulk modulus of elasticity. Now we had discussed Young's modulus of elasticity, and that was related to the change in configuration of length of any material. Now the bulk modulus of elasticity is related to change in volume of any substance. Now you can consider, we are having a figure in which we are considering an object which is a solid object. Now we are applying force on this object from all the sides. So P is the force applied over here, and what we are observing that F is the force applied over the area A. So we are pressurizing this object normally perpendicularly over the surface, and we are compressing this, and the new object is having volume slightly less than the initial object. So the change in volume, this object is delta V, and the new volume is V minus delta V. So the bulk modulus of elasticity for this wire will be given by that the ratio of normal stress to the volumetric strain. and the formula for this is stress is force upon area and the volumetric strain is delta V upon V. Now this bulk modulus of elasticity is equals to minus F upon A delta V upon V. This negative sign shows that the volume of the object is reduced by application of the force. Now rearranging the terms, and we are getting that this kappa bulk modulus of elasticity is minus P into original volume divided by the change in volume. Now this P is the pressure, normal pressure exerted on this surface. Now SI unit for this bulk modulus of elasticity is Newton per meter square or Pascal, as the unit for pressure is Newton per meter square, and we know that strain is having no unit. Now the dimensional formula for this bulk modulus of elasticity is M L minus 1 T minus 2. Now after this, let us discuss what is compressibility, because we are applying force on this surface and we are compressing the object in order to obtain the bulk modulus of elasticity. So this compressibility is the reciprocal of the bulk modulus of material. Now the SI unit for this compressibility will be per Newton meter square, that is the reciprocal of the SI unit for this bulk modulus of elasticity. Now after this bulk modulus of elasticity, our next topic is the modulus of rigidity, that is the object is rigid to a fixed base, the lower base of the object is fixed, and we are discussing the shear modulus. Now what we are having in that, what is this shear modulus of a particular substance? For that, let us consider the figures. In the first figure, we are having an object, that is a cuboidal three-dimensional object which is fixed at lower face, and we are applying a tangential force F over its upper face whose area is A. Now an equal and opposite force F acts on its lower fixed face, which is taking it intact to this base. Now these two equal and opposite forces forms a sort of couple which exerts a torque over this cuboidal box. Now as the lower face of block is fixed, this couple shear the block into a parallelepiped by displacing this upper face to a distance A dash. You can see this in the lower picture, that the upper face is being displaced through a length A dash and other end D dash. Now this change in length is suppose delta T. Now we are having that AB is equals to DC, because these two sides were parallel of that cuboid, and suppose the length was L. So AB is equals to DC is equals to L, and the change in angle of this sheared face with respect to the base is A dash, and let that angle is theta. Now this is the definition for the shear modulus, that within the elastic limit the ratio of this tangential stress, that is we are applying to the tangential, the shear strain produced in this is known as the modulus of elasticity. Now you can write it as that shear strain, that is equals to this angle ABA dash is theta, because the change is in angle when we are applying the tangential force over the surface of this object, then the shear strain that the change produced in this object is with respect to the base, and that is the shift in the angle of the side with respect to its original position. So shear strain is equals to theta, that is nearly equals to tan theta. And let us finding out or substituting the value for tan theta from this triangle ABA dash, and this is equals to AA dash upon AB, and this is equals to, we know that AA dash is change in length and AB is our original length. So we are substituting the values and we are having that tangential stress is force upon area. So the modulus of rigidity eta is given by the tangential stress divided by the shear strain, and let us substitute the values. F upon A is our tangential stress and shear strain is theta. After substituting the values, we are getting that eta is equals to F upon A into L upon delta L. Now, this L upon delta L is dimensionless quantity. Both are having same dimensions and same units. So, the SI unit for this modulus of rigidity is Newton per meter square, and the dimension formula is again m L minus 1 T minus 2. Now this shear modulus of a material is always less than its Young's modulus, and it shows that it is easy to slide the layer of atoms of a solid substance over one another than to pull them apart or to squeeze them closer to each other. So always, because we need a less amount of force in that case when we are sliding the layer of a solid substance over one another. Now the elastic deformations produced in all the bodies become the plastic deformation with time. So with the passage of time, the object which is showing the elastic behavior becomes the plastic, and only solids have length and shape. So Young's modulus and shear modulus are relevant only for the solids. And we know that the solid, liquids and gases, they all have volume elasticity. So this bulk modulus is relevant for all the three states of matters, that is gases, liquids and solids. And point to be remembered is that the metals have large value of Young's modulus than the alloys and elastomers. And these materials having the large Young's modulus, they need large amount of force to produce a small change in length. In our day-to-day life, we say that the substance or materials which stretch more are called more elastic. But this effect is known as the misnomer, and the material which stretch to lesser extent for a given load, they are considered to be more elastic in terms of physics. So in our day-to-day life and in our physics, we are having two different explanations for the elastic substances. So these are the points to be kept in mind while we are discussing the elastic behavior of the materials. Now let us discuss further some other elastic effects. Now what are these? First one is elastic after effect. Now as the name suggests, elasticity after the effect, that is the force. So the delay in regaining its original state by a body when the deforming force is being removed is called the elastic after effect. The bodies return to their original state on removal of deforming force, but some bodies return immediately after removal of the force, while some bodies take a longer time to do so. So these are the elastic after effect after the removal of the force. Like we can consider the example of quads. We know that quads are highly elastic in nature. So when we are removing the deforming force from quads, they regain their original configuration immediately. But on the other hand, a glass fiber takes many hours to regain its original state. So these are the elastic after effect for different kind of materials. And you can see from this figure that we are having a wire which is suspended to a fixed end, and what we are having here, that we are having oscillations of a torsion pendulum. Now we'll discuss these oscillations in the elastic fatigue. As the name suggests, fatigue means that is tired. So elastic fatigue is defined as the loss in length of a material that is caused due to repeated alternate strain in the material. Now, during this vibrations for this torsion pendulum, the wire is subjected to repeated alternating strains. And if we set the wire into torsion vibrations, this wire which is attached to this disc continuously vibrate for a longer time. And what happens, as we know that energy of any substance dissipate, in that case the object is not able to regain its original configuration. So due to the continuous alternating strain, the wire is said to be having tired or fatigue. So if we are having a hard wire, that can be broken by bending it repeatedly in opposite direction, because it loses its strength due to elastic fatigue. Now the next is our elastic hysteresis, and this is, we can understand from this figure that the object is not retracing its stress strain curve after the removal of force. So we are applying force on the object is tracing the path from O to A to B, and when we are reducing the force, the object is coming back to its original configuration, that is O, but through a different path, that is BCO. Now we are having so many applications of elasticity. Like we are having metallic ropes. We consider metallic ropes. So the thickness of metallic ropes is used in crane to lift the heavy loads, and we decide the thickness by the knowledge of elastic limit of the material and the factors of safety. Next example is the bridge designs. Now by knowledge of elasticity, we can design the bridges. So the knowledge of elasticity is applied to do the designing of bridge, and it does not bend. Like the material we are using in the bridges should not bend too much or break under the load of traffic and the force of wind and with its own weight. So many weights are exerting on that bridge. So with these forces, it should not bend beyond a certain limit. And you can consider this from this figure, that the weight is tight. Now if we are walking on that, we are applying the weight downward. Its own weight is also there. So when a load W is suspended at the middle, the bar, that this bar get depressed by an amount. and the bending can be reduced by reducing the material which is having the large Young's modulus. So we can have a better choice and we can use the buckled bar, that is the I-shaped bar having the cross section of I shape, in order to provide a large load bearing surface which is having enough depth. And you can see it from this figure that we are having I-shaped bars. Now the maximum height of mountain on earth is also depends upon the shear modulus of the rock, and the hollow shaft is stronger than a solid shaft which is made up of the same quantity of material. So a torque is required to produce a unit twist in that particular material whose modulus of rigidity is given by eta. Now, after discussing the applications of elasticity, our next topic is elastic potential energy of a stretched wire. So, if we are applying force on any length of a wire, in that case, we are having increase in the length of that wire. Now, let the force F is applied on the wire, and that force is increasing the length by the amount delta L. So the increase in length is delta L, and the new length of the wire becomes here L plus delta L. Now the average force, that is average internal force acting on the object, is F by 2, and our work done due to this force will be, as we know that force into displacement is our work done, so work done on the wire, that is the average work done on wire, is change in length upon into the force applied. Now we are applying this formula and we are getting the potential energy for this elastic object is U. As we know that the work done is stored as the elastic potential energy in a given wire. So U is 1 by 2 into the force applied into the increase in length, and this is equals to stretching force into increase in length multiplied by 1 by 2. Now let A be the area increase in the wire. In that case, our potential energy is equals to, we are just arranging the terms, F upon A into delta L upon L into AL, and this comes out to be 1 by 2 stress into strain into the volume of the wire, and this potential energy per unit volume, that is symbol is small u, is equals to U upon volume, and that is equals to 1 by 2 into stress into strain, and this is equals to 1 by 2, that is half of the Young's modulus into strain square. So this is the relation what we are obtaining for the potential energy. Now our next topic is the Poisson's ratio. What is this Poisson's ratio? So for that we are having, within elastic limit, the ratio of lateral strain to the longitudinal strain is called the Poisson's ratio. Now what is this lateral strain? The strain produced in the direction of applied force along the length is known as longitudinal strain, and if we are applying the force and the strain is produced perpendicular to the direction, that is perpendicular to the surface, then it is known as the lateral strain. So for that let us consider that we are having a wire initially of length L, and when we are loading this wire, the increase in length is delta L, and D is the initial diameter of the wire, and when we are loading this wire, then there is change in the diameter, that is delta D, and new diameter of the wire is D minus delta D, because we know that when we are applying the load, so there is thinning of the wire becomes thin, so there is reduce in the diameter of the wire. Now the longitudinal strain produced in the wire is delta L upon L, and the lateral strain produced is delta D upon D. Now the negative sign is associated, so lateral strain is minus D by D, and negative sign is that this is decreased, that the strain is or diameter is decreased. So the Poisson's ratio is sigma is equals to lateral strain upon the longitudinal strain, and after substituting the values we are getting that this is equals to delta D by delta L into minus L upon D. Now this is negative sign shows that the longitudinal strain and the lateral strain are in opposite sense. As we had discussed, the length is decreased but the diameter is increased but the diameter is decreased. And the Poisson's ratio, being a ratio of two strains, is a dimensionless and a unitless quantity. So with this topic your chapter is being concluded. Go through the chapter and solve the numericals based on the